Imagine you and a stranger in another city both click buy on the exact same movie seat at the exact same millisecond. Who actually gets the ticket? Behind the scenes, the theater's computer system is fielding millions of these overlapping requests. To handle the traffic without double booking, the system relies on a process called concurrency control. The goal here is something called serializability. Think of the server like a master builder managing a construction site. Instead of letting all the workers pour concrete and lay bricks at the exact same time, the builder forces them to take turns, doing one job after the other. If the server didn't step in to direct traffic like this, the illusion of seamless digital multitasking would collapse, leaving us with scrambled and conflicting data. To see what scrambled data looks like, imagine two artists trying to paint different pictures on the exact same physical canvas at the same time. If the first artist spends 10 minutes carefully painting a tree, but the second artist immediately slaps blue sky paint right over it, that tree is gone. In the digital world, this is a lost right. One person's saved work is destroyed by the next person's. Now imagine someone walking by and trying to buy the painting while it's still a chaotic, half-finished mess. If you make a decision based on looking at incomplete work, that's what developers call a dirty read. Or say you look at the canvas, look away for 2 seconds, and look back, only to find the entire picture has changed because the artists are still fighting over it. This shifting reality is known as an unrepeatable read. When these physical scenarios happen inside a computer system, they corrupt the information we rely on every day. Keeping these specific errors, the lost writes, the dirty reads, and the unrepeatable reads, from happening is the main job of any database server. To keep our data safe while it's being updated, we need a way to block out distractions. It is like snapping a heavy padlock onto a private diary so no one else can open it while you write. Computer servers do exactly this. Before a server starts updating a piece of information, like a bank account balance, it places a digital lock on that specific file. There are two main types of these digital padlocks. A shared lock is a rule that says multiple people are allowed to open the book and read the data at the same time, but nobody is allowed to change the text. An exclusive lock is much stricter. It grants just one single user the power to read and rewrite the data, locking out everyone else until the job is done. These digital padlocks protect our information, but if a server just hands them out randomly without a strict schedule, everything will grind to a halt. To keep things moving, servers follow a strict rulebook called two-phase locking. This rulebook breaks every operation into 2 steps. In phase 1, the growing phase, the computer must gather every single padlock it needs for the entire job before it actually does any of the work. Then comes phase 2, the shrinking phase. Once the work is finished, the computer gradually releases those locks so others can take their turn. This chart shows 2 different ways a computer might handle these locks. Looking at the left column, Schedule SA, we can see a mistake. The computer unclicks a padlock on one book, but then immediately tries to grab a new padlock for a different book. This breaks the golden rule. If we look over at the right column, Schedule SB, we see a successful operation. Here, the computer gathers all its locks first, ensuring it has everything it needs before it starts letting go of anything. Following this exact sequence of gathering and releasing locks keeps the list of tasks organized. It ensures that even with millions of things happening at once, every piece of data is handled in a predictable order. Even with a perfect schedule, the locks themselves can occasionally create a block in the system. It is like 2 stubborn kids on a playground. One has a red toy, the other has a blue toy. They both want what the other person has, but neither is willing to let go of their own toy first. This happens in the digital world when one computer locks a file and waits for a second one, while another computer locks that second file and waits for the first. This circular wait is called a deadlock. Servers run deadlock detection, scanning the network for these trapped loops. Once found, the system steps in. It cancels one victim operation, stripping its locks so the other computer can finish. Canceling that one operation is the necessary sacrifice to break the stalemate. By doing so, the server keeps the rest of the digital system functioning. From stopping artists from ruining a canvas to forcing stubborn computers to share their toys, concurrency control keeps the digital world turning. Next time, we'll look at what happens when the machines actually break down as we dive into system reliability and failure mechanics.